Hello everyone. I know just a few moments are remaining before the lecture begins. The question that I asked earlier was till now for you guys, please put down in chats what problem you guys are facing regarding natural language processing. It is okay. You could be confused about any of the things. Just put them down in chats and we'll try our best that we'll clear your doubts. Okay. So feel free. We'll start in just 2 minutes. Okay. Good good evening everyone. So today this is me, Prashant. I'm joined by Diptesh, and also we have with us Professor Amit Sethi. Let me first tell you before we begin that the goal for us today is to make you guys comfortable with how you process languages in the context of deep learning. In this lecture, we'll be giving you intuition in terms of how the processing for natural language is done, and that will clear a lot of your doubts when you're looking for resources, reading papers, etc. So don't worry, feel free to put doubts in the chats and we'll be sure to help you guys. Okay, let's begin. The agenda for today is we'll be talking about the NLP pipeline in the context of text classification. We will see how text is represented before we feed it to our model, which in this case is a deep learning model or a neural network in putting simply. We will see what are the modern approaches to the text classification, which you guys might have known if you guys are reading around on the internet, some mystical thing which is called as word embeddings. And we'll look at how the approaches that we are going to talk about even work when you are dealing with challenging problems such as name entity recognition or part of speech taggings. Don't worry, these problems, yes, they are tough, but not as alien as they might sound right now. All right, let's begin. So, see, when dealing with anything in natural language processing, there is a certain aspect to through which you should look at languages. When you're talking about images, it is just what your eyes are looking at. Yes, there are multiple facets involved when our eyes as humans are processing visual information. But language is because put down in words has many hidden meanings, hidden semantics, and a lot of complex emotions are captured in text. That is why it is relatively difficult for making computers understand languages. Now, to make that process easier, the language we look at language in a layered manner. This layer is same for speech processing also. Now, to explain that, I will hand over to Diptesh, who is with us, who will explain these layers. So, over to Diptesh.
Good evening, everyone. I hope I'm audible to everyone. So, if you look at this layer, the bottommost segment is morphology. Then you have post tagging. Then you have chunking, parsing, semantics extraction, and finally, at the last level, you have discourse and co-reference. Why is this layer being put in such a manner is something that I'll try and explain to you. Morphology is something that is processed or performed at a very basic word level. So when you try to process language and try to make computers understand language, you try to look at the words, then the structure in which the words have been put in a sentence or a phrase, and then you go on and try to look at its semantics. Of course, some of you who are already aware of how natural language processing is being, the problem of NLP is being tackled in today's day and age, might feel that statistical methods are doing far better than what classical methods used to do, and we don't really need to look at the morphology, or we don't really need to pause tag everything, so that you know what, we can get to the semantics of the sentence. Or if you want to tackle a problem like sentiment analysis, then you probably don't need to do all this. But the way this image has been put, the way these layers have been built, there is a reason for that. Now when you look at the segment of morphology, the task of analyzing a sentence morphologically or performing morphological analysis is something that comes at the very base level. What morphological analysis is when you have a word, move on, like try, and when it's represented in its past form, tried, so the y at the end of try is basically replaced by ied. What a perfect morphological analyzer should be able to do is ensure that a root form of the word is extracted from the inflected word tried, or at the very least the inflection is cut off. So you can get, maybe if you use a lemmatizer instead of a morphological analyzer, maybe you will get tr, maybe you will get try. But if perfect morphological analysis is talked about, then it is something that will give you a representation of try as the root word and ied as the inflection on it. Similarly for the words visible, invisible, create, recreate. And I would like to give you an example of a Hindi word, karna. So let's just go to this link that I have put here in this slide. This is the Hindi WordNet, where the senses, the different senses of the word. Hindi WordNet is basically a knowledge graph. We have not conducted a lecture on knowledge graphs yet. Let's not get into that. But let's just try and think of this as a dictionary which can represent word synonyms and word senses to you. Okay, so if you look at it, Prashant, if you can just scroll down a little, you have 18 different verb senses for the word karna. So you might say कार्य करना, और या फिर काम निपटाना, और काम करना. These these different word senses come into play. And when morphology is talked about, kar, the word kar itself can have different inflections on it, and those inflections can lead to different senses. So morphological analysis for a word is basically something that can even change the meaning of a word. Okay, let's go back to the slide. Let's talk about pause tagging now. Now that you have understood that lemmatization or morphological analysis is something that you do at a word level, let's talk about pause tagging. Now, pause tagging is something that is done either at, let us say, sentence level, to be fair. So what you do in the task of pause tagging is you try and associate each word with its gold label of part of speech. So the common part of speeches that are used in natural language processing are nouns, verbs, adverbs, and adjectives. Apart from that, of course, there are different kinds of nouns, there are different kinds of verbs. Pause tagging can be fine grained, the pause tags can be very fine grained as well. But these four pause tags are basically the most common pause tags. And for example, if you have the sentence Ram kicked the ball, so if you want to, if a perfect pause tagger sort of tags this whole sentence, then Ram will be tagged as a noun, kicked would be tagged as a verb, because morphological analyzer would have understood before post tagging that the word kicked has the root word kick in it, and ed is basically an inflection, and kick would be termed as a verb, then the would be a case marker, and ball would be another noun. Going back. Okay, so that is the task of post tagging. Then comes the task of chunking. Go back to that slide. Okay, so let us take the sentence, the book has many chapters. So when you perform the task of chunking, why do you need to perform the task of chunking is something a little more complicated. When you want to perform an NLP downstream task such as machine translation, which basically is translating one language into another, you would want to take the syntactical structure of the sentence into account. You would want to know if this particular language has the word order, follows the word order of subject verb object or subject object verb. Just a minute homework here. I don't know if you know this or not. Try and find out what word order does English follow and what word order does Hindi follow. That may clear this up for you. So syntactically, both English and Hindi follow different word orders, and the tasks of chunking and parsing, basically what they give you is the the tree format, or the subtree. For chunking gives you a subtree format of the, let us say the sentence is the book has many chapters, so the book would be a single chunk, many chapters would be a single would be another chunk. And when you parse this using a dependency parsing tree, then you would get the whole tree of the book has many chapters, and everything would be post tagged or dependency parsed along the tree. An interesting an interesting analogy here would be looking at noun compounds as well. So noun compounds, I don't want to throw a lot of terminology at you, but noun compounds are basically something which are noun compound phrases which give you an implicit relationship between two nouns. For example, student protest, apple pie. Apple pie basically means a pie made of apple. Student protest, a protest being held by the students. These are something, these implicit relations between two nouns can be tough for a natural language processing model to sort of understand. And hence, this is also a very nice separate problem when you start looking at linguistic, when you start looking at NLP problems linguistically. Now that we are done with chunking and parsing, semantics extraction is something that I am sure all of you would be aware of, because you already have had your lectures on word embeddings, you know about word vectors. So semantics extraction is something that follows the task of word sense disambiguation. Classically, this task has always been known as word sense disambiguation. And previously, the task of what the task of word sense disambiguation does is, for example, if you have a large corpus which is a document of sentences, each and every word should be marked. The word sense disambiguator or your model should be able to mark each word perfectly with its sense ID. So for example, if a sense, if there is a question, I will get back to you for sure. No, go back, Prashant. So if there is a word which occurs in a particular context, and in some other context it means something else, then the model should be able to recognize what the word means in this context, context one, or what the word means in context two. So semantics extraction is something that wordnets as knowledge graphs used to be employed for long back, but with the advent of word vectors and word embedding based methodologies, and especially with the growing neural network based methods, we have come up with, the natural language processing researchers have come up with, after word to vec we have seen glove, we have seen BERT, we have seen so many different language modeling based architectures. And hence semantic extraction is now in today's day and age is something that gives you a representation of a word in a large corpus on some dimensions. It could be 50 dimensions, 100 dimensions, 300 dimensions. The default is usually 300 for word to vec. This is basically a vector of how the word can be represented in a corpus. When you look at discourse and co-reference, this is the toughest layer of NLP. This is where the tasks such as sarcasm detection, co-reference resolutions are performed. And unless and until you do not have an understanding of the layers below and how from word level to sentence level the sentence has meant or how the sentence has structured, then you're probably not doing NLP, you're probably just into data science. I'm sorry, this is a distinction I had to make because uh, as an NLP researcher or as someone who is doing NLP purely, after you're done with your F scores and your precisions and your recalls, after you get whatever you want to, the most important thing is to get into what are your errors and why those errors occurred, why your model could not label or classify a particular instance into its correct class. And you may be able to notice or find a pattern. For example, your morphological analyzer is not working correctly, and that error is being thrown at the level of discourse. For example, your pause tags are not correct, and that error is being thrown at the level of discourse. So, this is something you should really know when you go ahead and do NLP. This is a very nice big picture. I hope you have understood. And of course, I can briefly tell you about pause tagging. I have questions here. Let me just try and take the questions while I'm speaking. Okay, the first question was, do we always need to do pre-processing like lemmatization? Look, that depends on the task. That entirely depends on the task. For example, if you are trying to perform unsupervised clustering of a corpus into different topics, then you probably don't need to do lemmatization. It might or might not help, but unsupervised methods don't really need you to go that deep. But if you are, for example, doing something as common as sentiment analysis, then when you look at a tweet, for example, unless you do not have the root words cut out of the morphologically inflexed words, like for example, I just said Ram kicked the ball. Unless you don't know what kick means, you wouldn't know what kicked means, right? So that is something lemmatization is going to help you with. It always depends on the task whether or not lemmatization is necessary. But for text classification, where root words can give you a better meaning representation, lemmatization should be done. Okay, now that question is done. Let me come to Ritik's question. Do we also covering sequence to sequence? Yes, an intuition shall be cleared for sec to sec models. Prashant will be talking about them. uh, Sir, won't the model get confused out in words which are in their natural form and contain ed at the end? Yes, exactly. That is why you perform morphological inflections, morphological analysis. If you don't lemmatize the words, the model will have different probabilities for the word kick and the word kicked and the word kicks. So you really want to lemmatize your tweets or whatever text which you will try and find a representation for. And of course, huge strides have been made into NLP now. There are word representation models like FastText, which almost eliminate the out of vocabulary word problem. Which means, the out of vocabulary word means when you would use word to vec and model a corpus for getting vectors, the word kick, if it appears in the word kicked, if it appears in the corpus, you could have gotten a vector for it. But the word kick, if it does not appear in the corpus, you would not get a vector for it. FastText, on the other hand, sort of resolves that issue. So uh, that problem has kind of been solved because subword based embeddings are also present in today's day and age. Okay, so I hope I have answered your question to a certain extent. If you still have a doubt, I will answer that in chat. Very briefly, can you tell about pause tagging? I will answer that in chat. I would want Prashant to continue with the presentation. Okay, at Saurabh reads text in. Okay, that is probably answer. Okay, I guess I'm done here. Thank you, everyone. Heading back to Prashant. Please continue.
Uh, okay, hello guys. I know that you guys have just witnessed a lot of information in terms of dealing with natural languages. Okay, just take a breath first and know this, that this was a very important piece of information. And if you guys are getting into the journey of natural language processing, either targeting a job or trying to get into research, you guys will be keep coming back to it again and again. Now I'll just give a 1 minute kind of an overview. See, in the beginning I introduced you guys, it is very difficult for making machines understand languages, but how research starts is on a very simple level, is on a in a simpler level. So as Diptesh already talked about, we are first looking at the morphology of the sentence, meaning what words there are, what inflections are present. So as an example, Ram kicked the ball. So Ram is present, then kicked is present. But morphological analysis will tell us, okay, fine, what would be the root form of that also, because then again, as shown in the wordnet example also, every work can have many variations. So we want to get to a common point. Then we talked about, okay, fine, we identified the words, what tags we associate it with. Now, what are the possible tags? It could be a noun, verb, adjective, etc. Once we are done with identifying each word, what we are trying to do at chunking and parsing is to see, okay, what is the structure that the sentence is following, different structure it can follow. So notice how we are going from word level information to a sentence level information. And after we know the structure of the information, we are talking about what sentiment it might hold. It is it positive, negative, and even beyond that, we want our machines to generate reasoning in terms of producing discourse. So that was kind of an overview. So understand this layered processing. Don't worry, no need to get everything right in first term, but if you are understanding this intuition, as the Tesh mentioned already, every challenge that you guys will be facing. And remember guys, if guys are working as an NLP guy in either job or research, you guys will be keep coming back to it, because you guys will find, let's say, sentiment analysis code on GitHub or Opens release codes, even good models from good research labs out there. But if you're trying to apply in different domains, so let's say someone has released in a domain of news articles, but you want to apply it to restaurant articles or some other domain, you will need this layered knowledge to be able to either build a good product out of it, or to even improve the research which is already being done. So again, very important. Anyway, let's come to text classification. Now I will present the whole pipeline, but before, let's look at some example. Why do we need text classification? See, in machine learning, you guys have been through what is classification. Just just providing categories to your input. That input could be, an image, or in this case, it is text. One very common example is the mails that you guys get in your Gmail account. Either it goes into your primary folder or it goes to spam. If you guys have carefully noticed it, you know that although Google spam classification is very good, but sometimes it does badly. So important mails will go into promotions folder, but not in input folder, inbox folder. So meaning, although it is used in introductory machine learning lectures, spam is a harder problem, and I want you guys to take a minute to understand it, because spam is nothing but a text, okay, lot of paragraphs. How do you know that the guy is talking about a scammy affair, or it is just a genuine mail to give you loan for your education? Okay, so even as humans, you'll guys have to understand nuances of text to be able to make the decision. And that is why computers also find it easy. Yes, there are approaches, and the layered approaches that we just talked about will help you guys if you guys are building your own spam classification system. Other is sentiment analysis. You guys have already seen in the previous lecture, but it also falls under the category of, given an input text, let's say a review on Amazon or for some product, can you guys build a model for saying whether what are the people emotions, positive, negative, neutral, very bad, or very good? Another very difficult problem right now, which is not fully solved, because even for humans it is hard, is fake news. The thing that you see on Facebooks, WhatsApp, different blogs, different news outlets. How do you verify that the information is correct or not? There is a whole pipeline on the back end also to, let's say, do some fact checking from you know uh, certified authorities. So let's say someone is saying that uh, XYZ actor died. Okay, now he might not be dead, he must be alive, but that information is out there, people are sharing that. But if some fact checking is done before, based on then a classification system can be built. Now this fake news can happen in multiple domains, and but see, it is a complicated problem, but it is again at the root, it is a classification task. Another non-trivial classification task is data filtering. So imagine you building, trying to build, let's say, a spam classification system only, or a sentiment analysis system. But see, okay, yes, when you guys are trying to learn, you guys will find a well formatted data set on Kaggle or someplace else. But if you guys are trying to build a new product, let's say in a company, or try to do research in a particular domain, more often than not, this reality will hit you that the data has some flaws. Either the data is not rich enough, meaning, let's say you find out the data for product reviews from Amazon. Okay, now this data can contain positive or negative sentiments, but what you want is more granular classification of the text. So you scrap data from let's say APIs or different websites, and then you build a model to perform classification in terms of not just positive, negative, but excellent, good, okay, or bad. So going from 2 categories to 3 categories, but to do that, you guys have to first fetch the data, first classify it either by building model, or some people can do it manually also. But even at that complicated task, which is non-trivial, classification comes into picture. Now, okay guys, just this slide, it is very important. This will clear all of it out, or even more all of the challenges which you guys have been thinking about in terms of the whole pipeline of how deep learning and NLP come together. Okay, so just look at it very carefully. On the left, you are seeing your raw text. Okay, whatever you get in any language that you get, then you form a representation out of it. Now, representation is the generic term when you're talking about, let's say, word vectors or different embeddings. Okay, so these quote unquote embeddings are nothing but a numerical representation of whatever text you have. Because see, at a root and at a very common sense level, try and understand that the computers only understand numbers, right? They can crunch numbers, they can manipulate numbers. Okay, but they don't understand the raw text. So that is why from text part, we are trying to do representation into number space. Now this representation can be of different form, which we will talk about. But if you guys have heard of some numbers, these are like one hot representation, word to vector, glove representation, fast text, even like BERT gives you a representation right now. So which are transformer based latest models by Google. So point being that go from basic to complicated, this fact remains same, that you have raw text, you're trying to represent it to a number domain, and then once you have made a numerical representation, it then just becomes a machine learning task which you guys have been already acquainted with, which is to do classification over it. I mean, quite simply, if I forget, if you guys just forget about text, if I give you guys just numbers and tell certain labels to it, let's say, okay, 0 1 0 1 0 1, you guys know that you guys will be able to build a classification algorithm and calculate the accuracy of it. But the problem comes when trying to understand that how to go from language to numerical representation. Many a times it is already being provided, and in many kind of debugging in that sense can be done once you understand the layered processing which we just told you. Now let's proceed in this regard. Okay, so text to a fixed representation, that fed to a classification algorithm, and out comes either a class label or some distribution or some regression. Okay, now let's talk about class labels first, that when talking about text classification, what it could mean. So see, generally two ways. Either the labels can be discrete, meaning So when you're talking about either the spam classification, incoming mail, whether it's spam or not spam, or sentiment analysis, positive sentiment, negative sentiment, neutral, okay, good or bad. Okay. So in case of binary, it will be just positive, negative. But from two binary meaning just two classes, multi-class classification meaning you are having multiple classes. So there an example of for sentiment analysis would be great, good, okay, bad. Okay, so it's not a binary classification problem, just an extension of that. Then multi-label classification, so trying to predict hashtags. Okay, in terms of, see, so don't get confused between multi-class and multi-label, because the only difference is that the in terms of multi-class the classifications is discrete, meaning that the category in which, so when you're talking about categorization of good, it can be, let's say, men's goods, women's goods on let's say Amazon. So the categorization is discrete, but multi-label generally it is pertaining to a similar domain, in this case the hashtag prediction. Many a times the label can be unknown, so there is a typo there, but then you can do text clustering, meaning when you get those numbers from the text representation which we previously just saw, now these numbers can be made cluster in that space, and in unsupervised methods in the machine learning lecture you guys have come across clustering algorithms, like trying to see k nearest neighbors, etc. So when you cluster them, the different cluster form a label in themselves. You can say it is cluster one, although you cannot say that this is, you know, positive or negative, but you can say there is cluster one, cluster two, cluster three. And this is happening when you're trying to discover how many categories there can be. Because let's say first sentiment spam or not spam you guys are aware of, but a very good example is this. Let's say a data, so it is not a natural language processing example, but let's say a data is collected about stars. Okay, and this you kind of you haven't named the constellations that this task belongs to this constellation, not, it is like a discovery process. So whatever data you guys have got, you represent it in numerical form, you do clustering, and now when clusters are formed you see that, okay, fine, these number of stars are close together, let's name it cluster 1 and the other cluster 2, cluster 3, and so on. Okay, so this process is of discovering new labels. Then there is continuous label thing, which is that, let's say I give you a person's CV. Okay, let's say someone is applying for a data science role and I give you a CV. Can, just by looking at information on the CV, can you guys say that what will be the salary of this guy? Okay, although this will model won't be behaving perfectly because of various reasons, but the point is that even as a human, imagine, forget about computers for now, even as human, when you're looking at someone's resume or CV, you see, let's say the project section, you are seeing the what research he or she has done, what technology he or she knows. Okay, how they have structured their resume, is there a typo or not? Okay, have they have they have they mentioned the metrics of their project, or they're just talking in vague terms? So as a humans you can make many of the decisions on those factors. To a larger extent, for a machine also it can be done, and if you guys search, there are companies who are trying to do it. So it is not about 100% automation, but going from a manual automation to something which can be managed with the machine as well as humans, and this is true for any task to which machine learning is applied. Another is trying to predict the price of a product by its description. Okay, so a new phone launches, or a new spec phone, let's say, even is to be manufactured. The company tries to think that, okay, fine, what price do should we put? Yes, the raw cost is involved, but if the company is trying to estimate what more profit they can make, they can, you know, a model can be made in which, you know, input feature of the product description is put to the model, and we have, you know, lakhs of samples, and some price prediction can be made. Okay, and even as a human, just think for a moment that if I tell you that I got a phone of this, you know, this camera spec, this particular processor, this particular GPU, and I ask you guys that what would be the price range of that, because you guys have seen in your life that XYZ bought a Samsung phone for this price which had this features, someone bought a OnePlus phone with this specs for this feature, someone bought an iPhone, you guys will be able to put that price range, right? So that's what we are trying to automate also. Now, when we are done with the class level, let's look at classification algorithms. Okay, although it has been beaten to death till now to you guys, but yeah, I mean, classification algorithm from simple decision tree based algorithms, SVM, to neural based model, anything can be put here. Okay, now mostly in language processing, uh, different names are put to the model, but for very simply, just think about using entropy based methods or naive based even. So if you are using scikit-learn, you guys can find those models into scikit-learn linear model logistic regression, or using naive bayes. So as shown on the slide, scikit-learn naive bayes and multinomial naive bayes. So okay, so understand that labeling part is clear. Classification algorithm you guys have seen. Now let's get to the picture of where, you know, which is the main focus of NLP, that how do you represent text into numbers. Okay, see, text representation. Okay, if you guys have come across this term called feature engineering, you guys know that the way raw data is provided to you, even in case of numbers, okay, you kind of try to normalize the data. Okay, by normalize, I mean that, let's say you got people's salary. Okay, now salary can vary very vastly. You try to put it in a range, or even as probability, to depending on what task you want to perform. Text representation is a kind of feature engineering, okay, but done solely for text. Many, for as with any machine learning model, it is very possible that for languages also, as you saw when we are looking at the information layer by layer, going from word level information to a sentence level information, where in between we saw the structure of the sentence. Just by looking at that, you can construct some representation of numbers, that how good or bad the structure is, but that will be manual. What deep learning has tried to achieve on the onset of deep learning is to learn that representation automatically. But for even for many of the representation that you guys found, so for example, if you guys have heard about the glove representation out of Stanford, or even let's say you guys hear about the fast text representation or Muse, there are many. You will find that every one of these labs, what they have done is they have tried to create these text representation suited for a larger chunk of natural language processing tasks. Just take a moment to understand this, that if it would have been a very simple problem, then we wouldn't have been having so many text representation, either in forms of word to vector, which just, you know, intuitively means going from word to a vector representation, uh, glove, fast text, etc. Point is, when a new vector representation comes, some information of language is captured, let's say of the different kind of senses in which different words are there, or different variations of the words which can be there, as Diptesh mentioned in the earlier slides, that let's say for words like tried, for word to vec, it might not exist, only try exists. Okay, or even let's say tried exists, but the root form does not exist. For glove, there are many verbs which don't exist, for which vector representation don't exist. What do we do in that case? Previously we used to initialize them with 0 0 vectors and try to train our model. It should work decently, but as the space of deep learning in NLP is getting competitive, people want to capture these out of context words. Sorry, okay, this is a wrong statement. Not out of context, but out of vocabulary. We mean that whatever words your machine knows till now in the form of vector representation, if some new word comes, what are you going to do about it? So in that case, we break the word down by removing character after character till we find in our representation that, okay, is there a representation for this word? Now general statistics which can be there can be regarding text length variances, and these numbers can be calculated and used as representation. Then there are tagged word lists which can give you scores. So for example, sentiword, that if you guys can look up, will give you a sentiment label for every word that you can query to it. Okay, and similarly there are different dictionaries, quote unquote knowledge graph, which will be covering in the coming lectures. Don't worry too much about it, but just know that there is this API which exists to you, you can input a word to it and it will give you a relevant information. In this case, sentiment label, for some case it will be the POS tag, and for others other information regarding the sentence. Now syntactic feature, which is the information regarding how what is the content of the sentence and what are the different roles in which the words are present. Are they noun, are they verb, are they adjective? Those informations can also be used to construct your features. And then there are ad hoc features, like let's say you are analyzing for analyzing a tweet, okay, and trying to build a model. And these days, or even let's say WhatsApp chats, although that is private data, point being that lots of people are using emojis and lots of information is carried through that. And so can you, so let's say you're building a simple classifier that is the is the text formal or informal, okay. Generally in formal text you won't be finding emojis, but in informal text you will find that you can use emojis. So very simple case of building a classifier. So you can use this feature of counting the number of emojis in your training data. You can automate that and use that as a feature to your model. Now let's look at sparse text representation. Look at text representation first, that we are trying to represent words into numbers. Sparse meaning, we'll soon see why sparse. First approach is bag of words approach, which I know you guys have been you guys have come across, but in the context of this whole pipeline, let's go through it once more, which will clear the intuition of why we are using it. Okay, so let's consider this sentence of the quick brown fox jumps over over lazy dog. But let's we are replacing lazy by the, and we'll soon see why. So you have the sentence, the quick brown fox jumps over the dog, and there, okay, notice in the far right there is a dot also present, okay, which you will find in many of the sentences, many of the languages that you sorry, even if processing English or other languages, these kind of punctuation you will find commas, dot, let's say. Most of the time people remove it for the modeling purposes, but what can be done is even they can be used, because the placing of comma can give you additional information regarding how the sentence is structured, right? So okay, let's look at the, now see, this is just talking about one hot representation. Imagine that the English language consists of, I'm just guessing here, but let's say there are only 60,000 words, okay. Now you can you can prepare a vector, one hot vector of size 60,000, but that does not happen. Generally the corpus that you are analyzing, so let's say it is for sentiment analysis only, or it is from tweets, okay, tweets to sentiment, that analyzing tweets for sentiment. Imagine this, that when you are analyzing tweet, it is 140 characters limit, so limited number of words are used by people. The corpus that you are having will contain not a universal infinite words, but a limited set of words, okay. So let's say it is containing about 1,000 different words, and using those 1,000, those tweets are present in your corpus. Now in that case, the one hot vector size will be 1,000, placing one for each of the different verbs, okay, words. So in this case, let's say our vocabulary is simple, these nine tokens. I'm calling it as token. Why? Because not calling dot as a word. So the quick brown fox jumps over the dog. So 1, 2, 3, 4, 5, 6, 7, 8, 9. So the vector size is 9. I placed one using the, because I'm placing one at the first position, that will represent, I'm trying to represent the word the. Then 2 at the, for the word quick. Similarly 3 for, let's say, brown fox jumps over the dog, okay. So there are 9, there are 9 9 the vector size is 9, and it can happen that in your corpus there are about 10 to the power 5 different the size of your sample can be that. Now what will happen, very simply, don't need to make it a lot complicated, you sum everything, okay. So because the is repeated, you see a 2 here, and rest there is 1. When you sum it, you have a numerical representation, and then what you do is you apply a simple linear layer, which you guys have been seeing through, just a a simple hidden layer, and apply softmax over it, see the probability, assign a label. Okay, as simple as that. So going from this to the representation which can be classified. Okay, now what is the problem with this kind of approach? Okay, the problem is that the number of features, meaning the size of the vector that I'm talking about, calling quote unquote feature, can be as large as the vocabulary size. So think, as I told you guys, the number of vocabulary, number of words in the vocabulary in the corpus that you guys have can be on the order of lakhs. Okay, so 10 raised to the power 5, so even can go huge, millions, or crores. In that case, if you are using one hot representation, it will be off size 1 million for each of the word. How the hell are you guys going to process that? I mean, it will take a lot of compute time. Okay, and that is why, and that will make the model also difficult to learn, because the huge number space that you guys are trying to represent it, and try to learn from, let's say, using just the 10 hidden layer, or or 20, 100, even 200, 500 hidden layers, it won't be it, I mean, it is less likely, because even intuitively, if you guys think, initially you are going from a very large representation trying to go to a very smaller representation, lot of information loss will be there. Also, there is absence of context, meaning if you look at, you are providing one for each word wherever each word is present. Okay, but if you're talking about, let's say, okay, look at this sentence only, the fox is brown, right? Okay, as so what is brown? The fox is brown. Now in this case, you might feel that, okay, what is the need for the context? But let's imagine a case for sentiment analysis only. Yes, you can find the build a model with a decent labeling, that okay, fine, the sentiment are positive, negative, but if you want to analyze the analyze the text further, to see that because of which word the sentiment is positive or negative, now that information cannot be captured by the model if the context is not taken into account. And by context, what do I mean? If I'm considering the word fox, I should use some information from brown to capture some information that the fox is brown, and let's say jump also, which will capture that okay, the fox is jumping. Very simply, it can be done by trying to group multiple words at a time, meaning when you're just considering one word at a time, it is called a unigram model. When you're considering two word at a time, it is called a bigram model. Three word at a time, trigram model. Okay, so very simple case, okay, to include context. Also, in this case, the problem is that all words are being treated identically, right? I mean, it is a generalized statement for the being absence of context, that when I'm talking about fox, I'm not considering the information from brown or the fact that the fox is there to jump. Okay, so that is why treating the words independently might not make any sense. Because imagine this, if me and you are talking, and I just say a word fox to you. Okay, what do you make out of it? You will ask me what the fox is doing or what color of the fox is. Okay, although you might be aware of the color of the fox because of your past representation in your own head, because let's say you watch Discovery, etc. My point is that the context in which the word is appearing, in this case fox, or other word also, just so for example dog also, these, every word, even if it is representing a person, animal, some representing some action which is jumping, every word will benefit from the context in which it is appearing. Okay, and different word embeddings that you guys see, they try to leverage that information to form that representation. So treating these issues is what is being done by different word embeddings that you guys see. So going from a large embeddings, in this case, if you are using one hot vector from, let's say, lakhs, a vector of size lakhs, you have glove vector, for example, which is of dimension from 50 to 100 to 300 also. Okay, now let's consider simple things, meaning, okay, fine, we are using one hot vector, what can we do with it? Okay, now these will apply to anything, even if you are using more rich vector representation also. Now see, not many words are important for the task. What do I mean by that? If I say that I went to the I went to XYZ restaurant, I ordered XYZ food, the food was great, or the food was bad. Okay, let's say this is the whole sentence. What happens is that most of the words if you're just doing a sentiment classification task, let's say, okay, it is not important to consider that I went to a restaurant, because it does not add any sentiment information to the final classification. So while trying to prepare the final numerical representation, I can try to attach weight to the vector representation of I went to the restaurant, and only consider those which have some positive negative sentiment attached to it, okay, while doing the pre-processing part, and then build a model on top of that. And that can be done automatically also. But just trying to give you an intuition that not every word is important for one particular task. That's why we associated weight to the word representation, in this case one hot representation, okay. And this weighing can be done based on length, okay, that what is the length of the different words based on the part of speech. So think about this, that if I'm just talking about uh, a sentiment classification, or let's say some just trying to talk about whether this sentence represents uh, some action or not, okay, meaning whether the, whether in that case some verb denoting action is present or not. Now this information, because part of speech tags are giving us whether noun is present, whether verb is present, adjective is present. Using that information to perform weighing on the input representation, word representation will give us capture better this information, that if I'm looking for presence of verb, my final numerical representation will capture that information. Why? Because I have used the weight of weight derived from part of speech, okay. And then there is TF-IDF, which you guys have already come across, using the term frequency. So in our corpus, let's say the words are coming everywhere, okay. So generally the words like the are everywhere, okay, but they don't tell any extra information most of the time, okay. So assigning a less weight to them, okay, and assigning larger weight to those who are infrequent. Now how do you take care of the context, okay? Think about this. I already told you guys that when we are considering only one word at a time, it is a unigram model. So don't be confused by the name. Just see that considering just one word at a time. You take the vector representation, either one hot vector representation or any of the modern numerical representation, embedding based representation, from fast text, from BERT, anything. You get a numerical representation. You sum them up. Because it is one hot vector, you're seeing that after summing up it is 2 1 0 0 1, and then you get a linear layer and get a probability out of it, okay. Now if we are just using, let's say, one hot vector only, how do we capture the context? So as can be seen, we consider the bigram, meaning that two words at a time. So the quick brown fox jumps over the dog and dot, okay. So what will happen is that now when you're trying to feed to the model, what you will be doing is you will get a one hot representation for the, you will get a one hot representation for quick, and let's say you sum them up, okay. Now this summing is supposed to capture very simply the information regarding both of these words. So here you can see that I told you guys that when talking about fox, the information regarding brown is not present, but now because you are using both of these information before feeding into the model, that information is captured even regarding what is the fox doing. So fox is jumping, okay. So the next bigram, which is capturing fox and jumps, will capture that information, okay. So don't look at this pipeline in a very complicated manner. Just look at what is happening actually. You are just considering words, trying to get a numerical representation. Now to get the context information, you are considering the numerical representation of the previous words, okay. In this case, considering two words at a time for this input sentence, you get the context. And similarly it can be trigram also. So that will be the quick brown fox, or brown fox jumps, okay. That will capture some more context. Yes, you will guys have to see a trade-off in where you guys have unigram or bigram, or can use trigram also, okay. Now let's talk about dense representation, okay. So see why we're talking about it is sparse, okay, because this representation in terms of numbers is not capturing much information regarding the words that are there. Now dense representation means, and that because it is generally prepared using a neural network, So for example, Glove et al. Tried to learn the numerical representation using a neural network. Okay, so it goes from a one-hot representation to a numerical, a float representation for every dimension. Okay, so it can be on the order of 10 raised to the power 3. Why 10 raised to the power 3? The recent representation from Elmo, quote unquote Elmo, you guys can look it up. It gives you a representation of size 1024. Okay, so every word will be represented with numbers of the size 1024. Every placeholder will have a float value. Now what that this numbers represent is a vector. Now as you guys know from mathematics, the representation of vector in some space is capturing some information. In this case, what is that information? That information is about the words existing in our language. Now as I told you, this representation, vector representation, is learned differently. So most of the time for the task and the severity of it, you guys used an experiment with different vectors. So what happens is that you try with word to vex, see how the model is behaving. You try with glove, you try with Elmo. Most of the time, depending on how simple or complicated your task is. So let's say you are just doing classification, you know, even word to vec or glove might perform decently. Okay, but you are doing more complicated things. So for example, let's say you're trying to generate, you are trying to do machine translation. Okay, so trying to generate new tokens. Okay, in that case, the representation of glove might not perform very well. So that's why we use more modern representation. So that mean why I give you guys this example, because depending on the task, the representation matters. It can be simplistic, you don't need not overcomplicate it, but for complicated tasks, yes, there are good representation that needs to be learned. So one thing to note is that this representation, because they are learned smartly, you're not storing, let's say, millions of numbers. You're just storing on the order of 1,000, which is very low, very small, and still capturing a lot of the meaning. And in case of glove, it can go as small as a vector of size 300, 100, or even 50. Okay, for one particular task, any particular task, I encourage you guys that if you're using glove, you guys try with different representation and see how good or bad the model is behaving. Okay, now see, because you guys already saw the pipeline of neural modeling in NLP, it is the same. Previously, we were getting from word to a one-hot representation. In this case, we are getting a neural representation in terms of any vector that we get. We again use this representation to either sum them up, to find a mean, max, whatever, and then get a final representation for the whole sentence. When we get the final representation, we just apply. Think about it. If every vector for every word is of the size 10 raised to the power 3, if you guys apply any aggregation function, finally also the aggregation, either sum, mean, max, will be of size 10 raised to the power 3. Then you apply a simple linear layer over it, apply a softmax, get a probability, do the classification, spam or not, sentiment or not. Okay, that you guys have been clear about. Just get the intuition. The more you get the intuition that how you are going from word to the numerical representation, and then till the linear layer, you guys already know what you are doing. So now see, either you can do the simple aggregation, or you can use weights also, right? Same principles apply here also, because in this case also the might not contain information regarding the sentiment. You can apply weights, and these weights can be the same one which you guys saw earlier, either based on length, based on the POS weights, or TF IDF. Okay, now, okay, so yeah, so what happens with these kind of representation, right? The feature space which I talked to you guys earlier, which can be as large as the number of vectors which are present, now is boiled down from going from a vector of size millions, which is called quote unquote features. Why? Because it is capturing the feature of the word. Okay, it can be the meaning or properties, the structure, etc. But it is capturing the feature of the word in a particular dimension. In case of glove, it can be a 50 dimensional vector, 100 dimensional vector, 300 dimensional vector. In case of Elmo, it will be 1024. Okay.
So, Prashant, is it like principal component analysis?
uh,
Are
Hello.
we like
Okay.
is it like PCA?
Okay, good that you said. Okay, so see, yes, what happens is that when you're talking about PCA, you're trying to get, if okay, if you see PCA, the representation we try to get is yes in a lower dimension. In case of getting to a lower dimension in terms of languages, yes, we are getting to a lower dimension, but the way in which you're doing in PCA, which is trying to project the vectors that you are getting, okay, or trying to get the vector space in a certain dimension for, let's say, an object, okay, object which is represented by certain vectors, that can be applied. That is one of the ways. But getting a lower vector representation, which is, as I said, can be learned using a neural network. Let me tell you what is the difference. Let me ask you this question. Did you guys attended the variational autoencoder lecture or tutorial? Hello?
Yes, yes.
Yeah. So yeah, the person who asked this question, did you attended the variational
Yeah.
autoencoder lecture?
Yes,
Yeah.
Prashant.
So if you remember there, what we were trying to do was, although we're not trying to do the PCA, right? PCA is just one of the ways to get a lower dimensional representation. There, what we were trying to do was using the help of neural network from going from uh, a large representation, okay, large size vector representation, to a lower size vector representation, where we're trying to make sure using the loss function, etc., that it will capture the necessary information about the input. You remember that concept, right?
Yes, Prashant.
Yes,
Yes.
and that is the similar thing which we see in case of word embeddings also. So yes, the intuition is same with PCA, that we are going from a higher dimension to a lower dimension, try to capture the relevant properties. PCA is one form of method of doing that, and here we are trying to do it using neural networks. So if you read the paper on glove or Elmo or any of the new method, you will be always seeing that instead of having a fixed feature, they're letting neural networks learn that representation, okay, just by doing the same thing, trying to do the back propagation, trying to use certain loss functions to capture certain properties. Same thing is being done, but the intuition is same, going from higher to lower dimension. Now for
So,
this, yeah,
yeah, Prashant. So
okay,
basically, the representation that is given here, like the
okay,
1,000 numbers that are given here,
okay,
they have some network behind them that is learning this.
yes,
Essentially,
yes.
at the start, you have to give the 10 power 5 words or whatever, and you pass it through some neural network, and these are the learned numbers, correct? According to the context or whatever,
Okay,
right?
yes. Okay, one thing to clarify is that in case of one hurt vector, what we were getting was that the number size finally you were getting was 10 raised to power 5 only. Now, what
Uh,
will happen is that, yes, you have initially 10 raised to power 5 words, yes, but when you are using, let's say, glove, Elmo, anything, after you process through that, every one of these words will have a dimension of what? From, let's say, 10
then,
10 raised to 5, and if you're using okay, imagine one hot vector, okay, you have a vocabulary size of 10 raised to power 5. Every vector, every vector for every word is of size 10 raised to power 5. What is the total size? 10 raised to power 5 cross 10 raised to power 5, okay, let's say this huge matrix you have. But now if you are using, let's say, glove of just the vector size 300, it will be 10 raised to power 5 words,
5
but
into
each word will be of size 300, okay.
300. Yes, right.
Yeah,
Yeah.
so that now, so that's why it's we this allows us to use external representation, so word to vec or glove. Also, words are not treated identically. Why? Because when these vector representation are being learned, either word to vec, glove, Elmo, anything, they are learned in a particular manner to capture context or even additional information, okay. In many cases the context can be very sparse, simple. Let's say glove was the first one, if I remember correctly, which used neural modeling for learning embeddings. Maybe Diptesh can correct me on that. But yeah, point being that from capturing the context information to capturing more complicated information, so just let's say, just initially looking at 5 words ahead of this word we are considering, 5 words behind. But in modern representation, you can consider a larger context, or the way you are processing the architectures. So we'll talk about it in the later slide. The way you are using RNNs, okay, to process it sequentially. it will capture additional information, which we'll talk about later. So how context is captured there, okay? And that is why, because that is captured, it, words are not treated identically, those context is being used, okay? Now this question often comes up, what kind of embedding should you use glove, elmo, whatever? But as I told you earlier also, it really depends on the task. There is no single recipe for that. If a task is very simple, see, your baseline model can be on word to vec, can be on glove. You can see how good or bad your model is behaving, because see, what trade-off you're making, right? From glove, in glove also you have three options: using a vector of size 50, 100, 300, capturing different layer of information. But if let's say using that model only, you're getting a model with 90% accuracy with decent precision and recall, you don't need to process further if, let's say, it solves a task. But let's say it is a critical task in a healthcare system, you need better performance of the model, then you can go to a larger vector representation, let's say elmo, okay? So really no single recipe, you guys need to try it, okay? Now let's go to what are the common things here, okay? The common problems, shared problems by both, are that the importance of weights for words are not fully defined, in the sense that which which what weight you apply to which word, okay? Do you handcraft it, okay? And the only way in which you are utilizing context for these model is to consider the vector representation of this word, that word also, okay? Why? Because see, when the vector representation is learned, it will be learned on a corpus. So let's say glove is learned on a corpus of size uh 1 million words, okay? Now this 1 million words are in different contexts, yes, but the sentence which is in front of you, it is not necessary that in vector representation it is lying close, right? So that is why the only way here is to use context, is again treat them as 1 gram by gram. But what can be done? We can learn these weights using neural network, good old neural network, right? How it is being done is that, say, consider a case of a simple multi-layer perceptron, that you guys are having the same sentence, you guys represent it as a vector. And one thing which you do is, in case of language specifically, that you add a padding vector. It can be a zero vector, okay? Mostly it is a zero vector. Why do you do that? Because let's say you're considering a task of sentiment analysis, one sentence is of size which consists 7 words, another contains 10 words, 15 words, 20 words, okay? Now when you are trying to build your model over it, how do you know at every time, are you how are you going to structure your network, okay, if you don't know the length of the sentence which is coming to you? Now that is why, before you do the processing of the network, you pad extra tokens to make every sentence of equal length, okay? So let's say the maximum size is of 20, which consists of 20 words. So, and there could be sentences containing of 5 words, 7 words, 10 words. You do padding so that every sentence can be containing of 20 tokens. I'm calling it tokens. Okay, it's not just me calling it. Generally, NLP research community talks about as tokens. So that the later structuring of your network becomes easier and the sentence becomes easier to process, okay? Now what then happens is that you concatenate everything. So let's say you get 300 dimension vector for the first word, second word, third word. You concatenate everything, and then you are applying linear layer over it, okay? So what happens is that the weights for different parts are learned, okay? But the problems is that what happens is that there is no parameter sharing and invariance captured. What do I mean by that? Going from one word to another word, what is happening is that still the context of that so for example, let's say you are at word jump, okay? What jumped? Okay, the fox jumped, okay? So the previous word context is not captured because you're concatenating, and because you're not using the information while processing which is obtained from the previous word, which the recurrent neural network solves, okay? Why? Because you do the computation on the first vector representation and then go to the next one. But when you're going to the next one, you are going to use the parameters which you learned for the previous word, and that is how in the end you are capturing the context. So that is how recurrent neural networks are helpful. Now let's see how they do in text classification. So imagine this is not a sentiment classification example, but imagine it is imagine it is a sequence of tokens and you're trying to predict a positive negative sentiments. How RNNs help? Okay, you take the first, and RNNs you guys have been through. It can be LSTM, GRU, different kind of unit. But what this unit does is nothing. You get the input representation. You again apply a weight over it, apply a function over it, get a hidden representation. So what will happen is this, that you get a vector representation. Let it be a vector of size 100. You apply a function over it, get a representation. Now when you are processing the next word at the next time step, which is quick, what you are feeding to the model is the context, is the output of the function which you are getting for the next one. So this is ht. Okay, at x1 consider this function ht. Now this function is applied over the previous hidden state as well as the input, current input. Okay, so in this case it is the fork, the, okay, my slide is I guess not visible, the quick. Yeah, so when processing quick, you are using the function which calculated the context based on the previous token, which was the same. When you are considering brown, you have, because you have calculated the function for the last two tokens, and it is captured in the last output of the last last token which is processed, which is quick. You are using that as the input with along with the input of the current token which is being considered. Okay, so it is a very sweet recurrence relation where at any time step t, you are considering the output of the previous state, which is captured by the hidden state ht minus 1, and the current input. Okay, and applying the function over it. Now see, if it is just a sentiment classification problem, so what is h8? It is nothing, but you are starting with the 0 token, you are applying the same function over it, and whatever you got, you are again considering the current token, applying the same function over it. So nice nested function processing you can see on the slide here. Point is that whatever representation you get in the end, it will capture the whole context of the sentence. Now you can apply a linear layer over it to get, let's say, a label out of it. Okay, this representation will capture the sequence in which we are seeing the sentence, or you can do a kind of averaging of all the hidden representation that you have got till now. Okay, and then apply your linear layer over it. So this is supposed to not just have a context which is captured in the end, but also additional information which is captured previously. Now why this is helpful, you guys will see more, let's say, in there will be a separate lecture for just sequence to sequence. After relationship extraction, it will be advanced LSTM plus attention. But you guys will see there is that if, let's say, I'm translating from English to French, okay, and I have calculated the hidden representation for every token while trying to translate in terms of an encoder decoder architecture, what will happen is that which word to use for translation. Okay, many times not every word is being translated, or some word will carry extra information. So we apply a attention weight over it, but not trying to complicate it, but just trying to give you guys an intuition that if it is just a simple classification task, you can classify by getting the representation in the end, or you guys can do some kind of weighting. But in this case, because you have passed it through a special structure, temporal structure called recurrent neural network, it will be capturing additional context information. And when you guys are doing some kind of averaging over that, it is supposed to give you a better modeling. Okay, in terms of machine translation, you guys can apply weight over it called attention weights to see which words are leading to better translation. Now what happens is that this was a one pass going from the first token to the end token. Same can be said when you're trying to capture the backward context also, because many times, think about, I mean, I don't have a right example right now here, but when going forward, you might find that you will stop at one point and you will look back. Why? Because the word which you just noticed relates to the word which you saw just a long back. That is why capturing not just the forward context, but also the backward context is important. So what you do is you first apply the same function which you are applying and calculate the forward context. Then you start from the last token which you calculated and again repeat the same process. but to capture the backward context. Once you capture both the forward and backward context, for every token, you use both the forward context as well as the backward context and simply concatenate it. So let's say the vector was of size 100. For forward it was 100. For backward it is 100. You use both the context for the word, and whatever hidden representation you are getting for the word for this token, you simply concatenate both of them, and then simply apply, same thing which we did earlier. Okay, max over it, min over it, or doing or even trying to let it learn through the model. Okay, so just try to get hold of the intuition. We started with the one hot vector, we used different vectors, then we try to capture the temporal context using this architecture, neural network architecture called recurrent neural networks. Then we try to not just use the forward context but the backward context, and then finally trying to construct a representation which will hopefully capture a better better information about the whole of the sentence, and then simply try to apply a linear layer over it to get what we want. Okay, now this is what is I hope this clear for most of you how the processing is being done. And whatever example you guys look at, either being sentiment analysis or even sequence labeling, so think about it. Okay, one thing I should clarify. So see, here we are just trying to, let's say, get a label. Okay, but think about this for a moment. Just think about this. Let's get simple. Okay, forget this for now. Okay, let's say you get the hidden representation, okay, for every token. Okay, now I tell you guys to do a NER to do NER tagging, or let's say part of speech tagging. So as Diptesh pointed out, possible part of speech can be noun, verb, adjective. Okay, now that would mean what? Every word in the sentence that is given to you can be any of these three categories. Now the task become much simpler if you guys get this neural pipeline and understand this, that once you are getting the numerical representation, okay, and that numerical representation going from a simple one hot vector to a dense representation to a representation which is learned by recurrent neural network, once you get that representation, you guys can treat it as a multi-class classification problem. Why? Because for every token, it can be lying in either of these three classes: a class of noun, class of verb, class of adjective. Okay, so what you need to do, instead of calculating the average over the whole context, you apply the linear layer over at every time step to predict that, okay, fine, if I've got a hidden representation for this word, apply, let's say, a simple linear layer over it, see how it behaves. Okay, and then for others also. So my point is that once you understand this structure, it becomes easier to see that how different tasks of either classification or even labeling are acting about. So NER and POS are nothing. NER is nothing but trying to understand name and entity, meaning that if, let's say, there is a Wikipedia entry about Sachin Tendulkar, and he played for BCCI, he played for different teams, etc., trying to understand and different players he played with, trying to understand which of the words are representing names and which are representing entities. It is a very important problem. You guys can read it about on Wikipedia entry, because imagine this. Okay, if I tell you guys that apple, the word apple, okay, apple can be a fruit, and apple is an organization, a company also, right? So you see that inherently in language, uh, this uh, this confusion is there because of ambiguity, that the word that you are considering, what it is. Okay, and name entity recognition is a very old problem. Yes, not perfectly solved problem, but my point is that it can be also modeled as a simple labeling task, which is nothing but trying to do a classification at every time step. And same with POS tagging. In POS tagging, what you're trying to do is trying to label every token as either the noun, verb, or adjective. Okay, yeah, with that I would like to end the lecture, and yeah, I guess we are done for the lecture. If you guys have any particular question, we can talk about that.
The Sir, I want to ask one question. The post tagging and the name entities are similar or somewhat different?
Okay, see, that's what I'm trying to tell you, right? See, if you look at the tasks themselves, historically how they have been treated. They are being treated as separate problem. But the underlying structure and what we're trying to do, that's what pattern I was trying to make you guys notice, that it is nothing. Let's say consider if I forget about name entity, okay, and forget about POS tags, okay. Finally, when you will be processing, let's say you're doing the task of name entity, what you will do, every word can either be a name or either be an entity, right? You will do a one or two label, you will apply a one or two label, apply a softmax every time step and see what label it has. Or when you're considering the POS tags, you will have a mapping of noun to, let's say, 1 0, verb to 1, adjective to 2, okay. And at every time step you are attaching a label of 0 1 or 2, and then at output seeing that, okay fine, if it is a 0 level, that means this the model predicted it's a noun. So my point is that on a, yes, the meaning of this task is different, that at one for one task you are just recognizing what is the name, what is the entity represented by the verb in the context that it is appearing, and the other you are trying to see that what role the word is playing, okay. So the language task meaning is different, but the modeling behavior is same, okay. Hope that clarifies something for you.
Like suppose post tagging tags a particular word and it assigns a noun or verb. So
Yeah.
how it gonna help the network, the model, in the feature extraction part?
Okay,
Like,
yeah. So wait, Diptesh will answer it more. Yeah. Okay.
actually, sir is already busy, I think.
Yeah. So actually, he's answering some questions on chat.
Uh,
Just give him a minute.
I,
Uh,
I'll ask a different
Okay,
question.
tell me.
okay, go ahead.
I- The lecture is over?
No, no,
Yes,
sir.
sir. Yes, sir. The lecture is over. We are just clearing some doubts for students.
Okay, go ahead.
I'll ask different question then
Okay.
further.
Okay.
Just can you go back to the previous slide? Previous this recurrent. So we pass each word separately. Like we first pass 100,9 the word
Okay.
and get the output of it and pass pass the information to the next word. Like so
Right.
the recurrent neural network just like doing that thing, like how particular word next word is dependent on the previous word, right?
Are you asking how it is dependent, or
Like I'm like thinking that it's a correct or wrong, like next word how it's depending upon the previous word, like
okay? It is less. Yes, some information. Okay. Let me give an example. Okay. Wait. Mm, not the sentiment class example, but okay. This is a perfect example. Let's say this is the sentence. Okay. Uh, in the internship exchange, this is a sentence. Okay. In the internship exchange program, the student came to India from Japan. Okay. He spoke fluent. If I say dash, okay, what will you say? Because he came from Japan, he must be speaking fluent Japanese, right? If he's
yes,
coming from France, must be speaking fluent French, right? Now,
yes,
as humans, we remember this context information that he's coming from Japan. Okay. Now, how do we make models remember such context? And that is why the structuring, the way in which we are processing in recurrent neural networks, in which when you are processing the current token, you are using the context of the previous tokens, and how that is being captured is just whenever the function is being applied. Look at this recurrence relation on the left, right? It is a very simple representation that at any time step t, whenever you are applying the function will be common for both, but the weight parameter is shared. It's shared amongst every time step. You are using whatever you calculated on the previous time step and the current input. And due to this nature, whenever you're trying to model, and the example that I just gave you, it is kind of a generation task, meaning you're trying to predict the next word. If I'm giving a filling the blanks task, you're trying to learn the model to predict that, okay fine, the person who came from France or Japan spoke fluent French, okay. That is how the context which is previously obtained is being useful, okay.
Okay, okay,
And I
got
guess
it.
your previous question was, can you repeat that, which we are going to ask to Diptesh? The question
Uh,
which you were asking?
the I forgot. How like pose?
Acha, okay, okay, got it. How pose was?
How pose like
Ah, yeah.
is used in the feature extraction? How helpful it is? Like
Hi, so Diptesh here. What I would like to say is that in again, I would repeat the same thing in today's day and age when semantic modeling using representations like BERT, etc., have become really advanced. Nobody really pause tags the sentences uh, with their part of speech tags while learning these representations, but there are still so you know how I'm not sure if you know how research goes, but n number of people try particular method for solving a problem. There is another set of people who are trying another method for solving a problem, and then people just, you know what, they try to keep improving on the method they feel is the best to tackle the problem. Now, when you talk about the use of pause tagging, previously the classical approaches of machine translation or the task of word sense disambiguation, they used pause tagging, the pause tags of words to ensure that they were tagging correct senses uh, with the words. Uh, the uh, the person who has asked this question, do you know about the task of word sense disambiguation?
no, no.
Okay, okay. So let me just start it from the very beginning. The task of word sense disambiguation is when you are given a corpus, you should be able to train a model, and the model should be able to tag each word with its correct sense. For example, let us take the Hindi word kar. Kar can also mean tax. Kar can also mean the karna wala sense, the something that is done. Okay,
Yeah, yeah.
so now the thing is, if the corpus sees karna, or when it lemmatizes, when it sees kar, it should be able to take into account the context and tag the word with the correct sense, because words have different senses, right? Now if you already have a pause tagged corpus, then you already have a clue as to what sense it can belong to, because it can belong to 5 different noun senses, or it can belong to 18 different verb senses. I showed you the example of cur on the wordnet website just
Yes,
now,
yes.
right? So if you already have a pause tagged word, then you can probably narrow down your classification of that word, that multi-class classification of that word, and hence it would become easier. Hence pause tagging was required previously. Pause tagging was used heavily. Right now also pause tags are used, but only by people who feel that these classical methods are still relevant. Most of the data scientists are using statistical methods, which is kind of sad for people like us, but I guess it's okay.
Okay, okay. This is Prashant again. Let me give you guys a more relevant example. Okay, not more relevant. That will be a rock choice of word. Choice of word. What Diptesh just explains is very important. So see, whatever he explained, it is not. It is not, as I told you earlier also. And the message with this lecture is, if you guys are going to go into jobs or research, any off the shelf model that you are trying to use for the task, you guys have to adapt to it. And I have a very good example right now. Let's say there was a previous model trained on, let's say, news articles. Okay, and let's say you're trying to use that model in the context of uh, movie reviews or restaurant reviews. Okay, now point is that the context is very different, the domain is different, going from general news to a particular context, particular domain called, let's say, restaurant reviews. What there happens is, or let's say we're talking about movie reviews, what there happens is that if you're just talking about classification, it can be done very simply. But let's say you're trying to use sequence to sequence model to generate reviews or something like the or the other, you would want to use the information that which actor was present in the movie from the movie description, to try to, let's say, try to build a rating classification system. What do I mean by that is, if a new Tom Cruise movie is coming up, the chances of it having a higher rating is higher than, let's say, some new actor is coming up, right? And that is what we as human also do. So from the corpus, you use this additional information that the information regarding actors which will be present in the reviews using which you are training a model will be helpful when you are building a model. Okay, so you pre-process your data, you see that which word represent the name of the person, which will be noun, and then use the relevant information. So let's say you have already from IMDb, you have a list of top 10 vectors, you assign some score to that, you use that in your corpus, and then build your model on top of that. So in movie, and similarly, this was just an example of actor. Let's say who is the director there, okay? Or in let's say in most of the time in India, what happens is that the Karan Johar, I guess, uses this a lot, that they will shoot movies in, outside location, so outside of India location, so they look exotic, and people go to watch movies, okay, because they are seeing exotic location. So at which location the movie was shot at? Was it shot at I mean, Switzerland, New Zealand, whatever? If outside location it is being shot at, the ratings can be adjusted accordingly. So a very practical example of why the POS tags of tagging these as names, or even using the name entity information, can be useful for the modern deep learning system, and is actually being useful. If I just quickly talk about the kind of research that is going on in our lab at IIT Bombay, so one of the students tried to build a model for sentiment analysis only, right? Now this sentiment analysis, if you're trying to build general sentiment analysis, most of the time it is not going to work. You will always need to build a sentiment analyzer for your particular context. Is it for a restaurant review? Is it for a movie review? Political. Okay, you're trying to do polling, that who will win, who will not. So what happens in this case is that when you're trying to build your model on top of the corpus that you're considering, you're trying to use the information which is present. So let's say I'm talking about restaurant reviews. So and I'm trying to find out reviews online and trying to pre-process the data to inform my model. In that case, what I'll do is I'm using the information regarding restaurant. So let's say someone is eating at Taj, and reviews are about that. Definitely, if your review is about Taj, from online reviews and from statistics, I can do a pre-processing calculation and try to give a score that these top 10 restaurant or 100 restaurant should inform the model that generally, if the sentiment is coming out of this, will be good or bad. If it is about certain kind of foods in the restaurant, okay, so let's say some restaurants are just known for veg or non-veg, that is being useful. If it is about, let's say, cricket analysis, okay, so there, let's say the bowler is bowling, or the batsman is hitting the ball in different directions, so different verb information which is present in the cricket commentary can be useful. So literally it is very modern. It is not traditionally it was relevant. Why? Because neural models were the feature was not learned by neural model. But even when the feature is learned by neural model, and because of the inherent complexity of languages which is present, the information whatever you can get from these resources regarding what is noun, what is entity representation, what is verb, what is adjective, this can be used to enhance your model information. And I will encourage you guys that after you guys get familiar with, let's say, 5 or 10 models that you guys train using just the word embedding, try to leverage the POS information, NER information, and try to see if it is improving a model or not. It will be a very interesting exercise. But just a very quick example that how these informations are useful. Hope that clears your doubt. Okay.
Uh, is there any architecture which uses the post tagging, like saving the all tags of the corpus and use in the letter, like how Grammarly uses?
Okay.
Is there an architecture?
Okay. So see, what question you're asking is, okay, I think you're got confused in the sense that, see, architecture and application are different. You rightly pointed out Grammarly uses that, right? Okay. Now Grammarly is leveraging that information and trying to model that, and it is trying to predict also that, okay, fine, the verb that you have, the verb form that you have written, it should be of this form. Okay. So my point is that your question should be clear in the sense that what can be the, okay, first question was what can be the application of POS tagging. That is cool. what question you're asking, I would say it is not complete, because by completion, what do I mean by that is using POS information to inform your model is very task dependent. So good that you brought the example of Grammarly. So for Grammarly task, the task of trying to correct how you're writing the sentences, it is both using the sentiment analysis thing also. If I don't know if you guys have premium Grammarly or not, so it, whenever you're even composing mail, it will tell you it is whether it is formal, informal, very friendly. So they're kind of trying to see different levels of sentiment. But when trying to do correction, it is trying correction of different forms. It is trying to leverage the it is trying to do the tagging part and use that information. Either mostly it can be manual, that from whatever verb forms we have been using, whether this guy is using current verb form or not. Okay, so my point is, it is very application dependent, that in your end-to-end pipeline, depending on the task, whether you are using this information or not. Okay, Grammarly is one such example. Restaurant example that I gave you is another example. If you are applying it for the cricket review, movie review, these are other examples. All right.
Yeah, got it. Thank you.
Yeah. Okay, guys.
Yeah, Prashant, I had one last one. Hello.
Yeah, go ahead. Go ahead.
Yeah, could you go to the last slide of the presentation where
Okay, where?
before? Yeah, this one. Yes. See, all this is clear. But then, when you pass it through the linear layer and you're doing the classification,
Right.
for suppose we're doing sentiment analysis, okay,
Okay.
and
Okay.
we're doing it on tweets. For suppose on
Right. Right. Right.
okay.
Right.
So, to for the back propagation and all that, we already need to know the sentiment of the tweet, right? Like some
Yes.
sentiment score
Yes.
over which
Yeah.
we opt.
Yeah. Yeah. Yeah.
Yeah.
Yeah.
So, when a person is tweeting, how do we know the sentiment score? Like,
Okay.
is
Okay.
there some other model which is making the sentiment score or
Okay.
something
Okay.
like that?
Okay. Fine that you asked this question. It is a very basic thing, but okay, understand this. If you have been through machine learning, you know that there are supervised, unsupervised way, right? Okay. Right.
Yeah.
Now, when you're talking about supervised machine learning, okay, and most of the methods are supervised, when you're trying to train a model, think about it. Forget about machine learning for now. If I give you 100 tweets, okay, and if I tell you, okay, I don't know what your name is. Can you repeat your name?
Jyoti Swaroop.
Okay, Jyoti Sarup. Hey, Jyoti. So let's say I'm giving 1,000 tweets, okay, and I'm telling you that Jyoti, uh, go through these 1,000 tweets and try to get a sense that what kind of tweets are representing, are positive in nature, in terms of sentiment, and what are negative. What will you do? You will read the first tweet, you will read the second tweet, etc., etc. But each tweet, when you're reading, you will try to remember some context or somewhere you have seen something, and you see that, okay, fine, this is positive, this is negative. Or let's say you're trying to teach it to a kid, let's say a 5-year-old kid who does not know Twitter, or who the kid who is still learning. You try to provide supervision to it. Same with machines also. When you're trying to build the model, okay, initially when you're trying to learn it, the labels are either provided or you put there. Okay, you get my point? So for every tweet that you downloaded for 1,000 tweets, before training the model, either let's say you're pulling data from Kaggle, okay, or even let's say you're manually preparing it for your own custom task, you will have to have initial set of labels. It can be on 500 sample, it can be on 100,000 samples. Those labels, why? Because no way the model will know what is the label until and unless it has seen certain examples and knows what kind of label it is, right? So this
Yes.
supervision part should have been clear in the machine learning lectures to you. But any machine learning task, and particularly supervised machine learning task, you need to provide those labels, without which you cannot let the model learn, right? You get that point?
Yeah. Yeah. Yeah.
Yeah. Okay, guys, so I hope things are clear. Don't worry. If you guys still have any doubts, please feel free to post on Campus Wire. Me and Diptesh will be very glad to point you to resources, more papers, and more things. I hope this was useful to you guys. Whatever Google form has been shared by Professor Amit Sethi, do fill them so that we get a sense of what we can improve. And with that, I will I'll end this. Sir, we are good to end this lecture.
Okay, thank you so much.
Thank you, sir. Thank you so much. Yeah.
Thank you, Professor, for giving us this opportunity.